Hello everyone and welcome back to Math Made Easy. In the previous lecture, we studied the Gauss Elimination Method, one of the most fundamental techniques for solving systems of linear equations. We learned how to convert a system into an upper triangular matrix using forward elimination and then determine the unknowns through back substitution. Although the method is efficient, but it has one limitations as well. After obtaining that upper triangular matrix, we still need an additional step, that is the back substitution, to calculate the values of the unknown variables. So that naturally raises an important question. Can we modify the elimination process so that the final matrix itself directly gives a solution, eliminating the need for the back substitution? And the answer is yes. And today's lecture is fully devoted to the Gauss-Jordan elimination method. And instead of stopping at an upper triangular matrix, this method continues the elimination process until all the elements above and below each pivot become zero, transforming the coefficient matrix into the identity matrix. Once this is achieved, the solution can be used or read directly from the last column of the augmented matrix. And this Gauss-Jordan method is widely used in solving the linear systems or finding the inverse of matrices and many computer algorithms. So let's just recall that final matrix obtained from the Gauss elimination method. From here, we had to perform the back substitution to determine the values of x, y, and z. Wouldn't it be more convenient if the matrix itself become this 1, 0, 0, become this 1, 0, 0, or some A, and the 0, 1, 0, some B, and the 0, 0, 1, some C. And in this form, the solution is immediately visible now. And this is exactly what the Gauss-Jordan method achieves. Basically, this Gauss-Jordan method extends the Gaussian elimination. Instead of eliminating all the elements below the pivot, we eliminate the elements both below and above the pivot. And our goal is to transform the coefficient matrix into the identity matrix. So basically, this process consists of three stages. First, we construct an augmented matrix, then use the elementary row operations until every pivot equals to 1, and then eliminate every element above and below each pivot. And the final matrix become this I and X, where this I is the identity matrix and X becomes the required solution. And the same three row operations are going to be used, interchanging two rows or maybe multiplying a row by a non-zero constant or replacing one row by itself or plus a multiple of another row. And these operations do not change the solution of the system. Remember that point. So what we have, writing this augmented matrix, choose the first pivot, make the pivot equals to 1 if necessary, make every other element in that column 0, move to the next pivot, repeat until the coefficient matrix becomes that identity matrix, and read the solution directly from the last column. So now we understand the theory behind the Gauss-Jordan elimination method. Let's just solve a quick problem. And this example is particularly with demonstrate how the method transforms the coefficient matrix into a identity matrix, allowing us to read the solution directly without performing the back substitution. So we have taken this augmented matrix. And this augmented matrix contains all the information required to solve the system. So our objective is to transform that left-hand side into the identity matrix. So now we have this first pivot as 2. And to make the calculations easier, we first convert the pivot into 2. That means we need to convert the first row as half of row 1. So this row becomes this 1 by 2, minus 1 by 2, 4. And hence your matrix becomes 1, half, minus half, 4, minus 3, minus 1, 2, minus 11, minus 2, 1, 2, minus 3. Now eliminate this minus 3. Hence, we are applying this row 2 as row 2 plus 3 row 1. So after calculating each entry, we got this R2 as 0, half, half and 1. And now eliminating minus 2. So for that, we have taken this R3 as this row third plus twice of row 1. Hence, we obtain this R3 as 0, 2, 1 and 5. And the matrix becomes this 1 half minus half 4. 0, half, half, 1, 0, 2, 1, 5. Now the first column has been completed. Now we move to the second pivot. Here we have the pivot as half. Make it equals to 1, no? Applying this R2 as twice of R2. Simply we get this R2 as 0, 1, 1, 2. And the matrix becomes 1 half minus half 4, 0, 1, 1, 2, 0, 2, 1, 5. Unlike that Gauss elimination method, here we eliminate both above and below the pivot. So we need to apply this R3 as R3 minus twice of R2. Then we got the results as this R3 equals to 0, 0, minus 1 and minus 1. Again, to eliminate this half above this pivot, this R1 becomes this R1 minus half of R2. And by that, we get this R1 as 1, 0, minus 1 and 3. And the matrix becomes 1, 0, minus 1, 3, 0, 1, 1, 2, 0, 0, minus 1, 1. Now notice the difference. In Gaussian elimination, we stopped here. But in the Gauss-Jordan method, we continue. Now the third pivot is minus 1. Simply making it equals to 1. Applying this R3 as negative of R3. So we get 0, 0, 1, minus 1. So the matrix become 1, 0, minus 1, 3, 0, 1, 1, 2, 0, 0, 1, minus 1. Now eliminating every entry above this third pivot. So to eliminate the 1 in row 2, we apply this R2 as R2 minus R3. And results we get as R2 becomes 0, 1, 0, 3. Now eliminating this minus 1 in row 1, applying this R1 as R1 plus R3. So we get this R1 as 1, 0, 0, 2. And hence the final matrix becomes this 1, 0, 0, 2, 0, 1, 0, 3, 0, 0, 1, minus 1. Now observe the left hand side carefully. It has become the identity matrix, and that means the last column directly contains the solution. That is this x equals to 2, y equals to 3 and z equals to minus 1. So no back substitution is required now. And if I substitute these values into the original equations, I get every equations all are satisfied. And hence this become our required solution. So today we started this Gauss-Jordan elimination method, one of the most powerful direct methods for solving system of linear equations. We began by understanding the motivation behind the method and saw how it extends the Gauss elimination method. We learned that instead of stopping after obtaining an upper triangular matrix, the Gauss-Jordan method continues the elimination process until the coefficient matrix is transformed into the identity matrix. We discussed the complete algorithm, performed the elementary row operations stepwise, solved a numerical example, and most importantly, we observed that no back substitution is required now, as the solution can be read directly from the final augmented matrix. So, if I just to compare these two methods, basically in Gauss elimination, we eliminate only the elements below each pivot and obtain an upper triangular matrix, and then using the back substitution to determine the unknowns. While in the Gauss-Jordan elimination method, we eliminate the elements both above and below each pivot and converting the coefficient matrix into the identity matrix and obtaining the solution directly. Both the methods are important in numerical analysis, but the choice between them depends on the nature of the problem and computational requirement. And in the next lecture, we'll study LU decomposition method instead of solving that system by repeated elimination every time. We will learn how to factor the coefficient matrix into the product of lower triangular matrix and an upper triangular matrix. And this decomposition is especially useful when solving multiple systems that having the same coefficient matrix but different constant vectors, making the computations much more efficient. So thank you for watching, and if you found this lecture helpful, please like the video and share it with your classmates and subscribe to MathMade Easy to continue learning numerical analysis through detailed theory, complete derivations and examples. Until then, keep learning, keep practicing and keep questioning, and I'll see you in the next lecture.